Today we want to talk about two more properties of waves that are exhibited by electromagnetic radiation. The first one's called diffraction. These two are going to kind of come together in just a few minutes, diffraction and interference. Diffraction we define as the spreading out of a wave around a barrier or through an opening. This is a photograph of diffraction actually happening with a water wave, right? Water waves are coming like this towards this opening, and as they go through this opening, what do you see? They spread out. They're not bending, they're not changing direction. That would be refraction. Refraction, Snell's law, right? This is diffraction, simply the spreading out of the wave as it goes through an opening or around a barrier. Now, that's a property of waves. Clearly, it's a property of waves. We can see it in that photograph happening to water waves. But it also is exhibited by electromagnetic radiation. Therefore, EMR must be a wave, right? What if we have two openings? What if we have two openings, or in this case, we actually have two sources of waves, which is the same as two openings? You can see that in the first one here, you would have waves going out like this. Now, you can't really see the second source, but if we were right here behind this guy's head, that would produce waves like this. Well, where a crest meets a crest, we get constructive interference. Where a trough meets a trough, we get constructive interference. Where a crest meets a trough, we get destructive interference. Notice the interference pattern that forms here. We get an area right here that is constructive interference. Big crest and big trough. Another one right here. Another one here and here and here. Bigger crests and bigger troughs. Bigger waves as a result of constructive interference. But notice in between there, we get these areas of destructive interference, the complete cancellation of these waves. It's calm, right? The water waves are not there. The water is just calm here and here and here. Constructive interference, destructive interference as a result of diffraction happening twice. Diffraction through two different openings, and then the waves that are spreading out through those two different openings interfering with each other. Clearly, that's a property of waves. We see it, a photograph of it happening with water waves. But that also happens with EMR. Therefore, EMR must be a wave. We're going to look at the interference and diffraction of EMR a little bit more closely now. If I had light going through those two openings as opposed to, let's say, water waves going through those two openings, what would I see? Well, at the top of the diagram here, you see a barrier right here. This is your barrier. You can see in that barrier are two openings right here and right here. There's light waves, red light waves in this case, going towards that barrier. But of course, those two openings in that barrier allow light waves to go through. The light going through that first barrier, or that first opening, I should say, diffracts. It spreads out, like the water waves did, right? The light going through the second opening also diffracts, spreads out, like the water waves. So, just like the water waves, these light waves produce an interference pattern. We have the crest and the crest of two different waves. You get constructive interference, trough and trough, constructive interference, crest and trough, destructive interference. You will get, just like in this diagram back here, these alternating lines of constructive and destructive interference. But with the light waves right here, these alternating lines of constructive and destructive interference, you can't actually see them looking from above. Right? If I look, in this diagram, I'm looking at this from above, right? I can clearly see the water waves interfering with each other constructively and destructively. When I look at the light from above, I can't see that because, well, as you know from your refraction lab, you can't see the light unless it reflects off of something. Remember when you shone the laser, right? You could see where it hit the glass block, where it came out of the glass block, but you couldn't see the light in between, right? Because it wasn't reflecting off of something. This is happening in here, but we're not going to see it because there's nothing to reflect off of. Does that make sense? Like, it's the exact same thing happening with the water. It's just that with the water we can see it, with the light we can't see it. So what we usually do with the light, in order to observe this interference pattern, is set up a screen down here, like a piece of paper or a cardboard or a piece of wood or whatever, plastic, whatever, that's going to act as a screen. Now, if I get an area of constructive interference in the middle, that means brighter light, right? Bigger crests and bigger troughs in the light. Brighter light. So that means on the screen, in that area of constructive interference right here, I'm going to get what we call a bright spot. You see that physically on the screen. You see that bright red spot. And then right next to it, remember back here we had alternating areas of constructive and destructive. Right here we have bright spot, and then we have, well, dark spot. Why? Because, well, this represents constructive interference, and this would represent right beside it an area of destructive interference, where the waves cancel out. And then beside that, constructive, and then beside that, destructive, and so on and so on and so on. So just like we had here, alternating areas of constructive and destructive interference, right here, we would also get alternating areas of constructive interference and destructive interference. We're just observing it in a different way. We're observing the interference here by looking at a screen, as opposed to just easily looking at it from above in this photograph. Does that make some sense? If you were to put some kind of screen here that measured intensity of light, or sorry, intensity of a water wave, like some kind of water wave detector that would plot for you the intensity of it, you would get the equivalent of a bright spot there, and then a dark spot, and then a bright spot, and then a dark spot. Alternating areas on that screen of bright spots and dark spots corresponding to the constructive and destructive interference here, just like we did right here. Now, if I plot a graph of intensity on the y-axis versus position on the x-axis, of what I see on that screen, then that middle bright spot right here, that middle bright spot that we're going to call our central bright spot, or our central, maybe a maximum, bright spot maximum, central, I don't know if you remember this term from Physics 20 or not, antinode, remember that? Bright spot, constructive interference, maximum, antinode, okay, whatever you want to call it, central bright spot, antinode, maximum, whatever, okay, it is the brightest. It is the most intense. You guys saw that when we just did our little demonstration, right? That middle one was the most intense. It was the brightest light. So you can see the intensity at our central maximum is highest. And then we get pretty much zero intensity because it's destructive interference, right? That would correspond to this spot right here. Okay, that first order minimum, that first dark spot, that first node, that first area of destructive interference. And then beside that, what do we get? Well, we get another area of constructive interference right here. But notice the intensity is lower. So going back to our demonstration again a minute ago, that second bright spot, the one that was beside this one, our central bright spot, that second bright spot would have been less intense than the first bright spot. And then so on, right? As we go out, we get bright spot, constructive interference, dark spot, destructive interference. Bright spot, constructive, but not as bright as the first, as the central one, dark spot. And then we get another bright spot, but not as dark or not as bright as the central one or the first one, and so on and so on and so on. Intensity versus position. This is a graph. This is not what you actually see. This is a graph. Okay, this is what you actually see. They both represent the same thing. When light or any wave passes through two openings, we will get diffraction taking place through both openings. You can see in this diagram here, we have monochromatic light, one color light, passing through these two openings in this barrier. You can see diffraction taking place as well. In fact, two diffraction patterns. When these diffraction patterns overlap, we get a phenomenon called? No. Dispersion relates to refraction, not not diffraction, right? When these diffraction patterns overlap, we get a phenomenon called interference. Now, we get areas of constructive interference where crest and crest meet or trough and trough meet, but we also get areas of destructive interference where crest meets trough. If we were to be able to see the interference that was taking place from overhead, then we would see a line of constructive interference right here. That would be big crests and big troughs resulting from crest and trough. But right beside it, we would see an area of destructive interference where crest met trough. We would see nothingness there, darkness, the absence of light. But then right beside that, we would get an area of constructive interference, then destructive, then constructive, and so on both sides. But here's the thing. If this is water waves, we can see this fine, right? Easily. We saw a picture of that yesterday. But if this is light waves, we can't see it because the light's not reflecting off of anything. So we have to add something in there for the light to reflect off of so that we can see it. We add a screen. This is our screen right here. This is what causes the light to reflect and allows us to see this interference pattern. If we had, Chase, a bright line right here that we couldn't see, it would form a bright spot on the screen right here. If we had, right next to that, destructive interference, then we would see a dark spot on the screen right here, and a bright spot as a result of constructive interference, and then a dark spot, and so on. So we look at that screen, and we see, as we saw for real yesterday with the laser and the diffraction grating, we would see bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, right? What's another name for the bright spot, by the way? Bright spot aura starts with an M. Maximum. Okay, what's another name for a bright spot or a maximum? Antinode, yes. Bright spot, maximum, antinode, all synonyms here. What's another name for bright spot? Bright spot, maximum, antinode, area of constructive interference. Okay, then the dark spots, dark spot, node, destructive interference. What's the M word that goes with that? Minimum. Okay, they all kind of go together there. We're going to call this one our central maximum, or our central bright spot. We're going to assign a number of 0 to it. First order maximum, or first order bright spot. Second order maximum, and then of course it's symmetrical on the other side as well. Let's label these variables now. Lambda is what? Lambda is the wavelength of the light. Okay, if it's monochromatic light, one color light, it's one particular wavelength of light. Usually visible light, usually 10 to the minus 7 meters. Not always. D, little d, is the, what's little d stand for? The distance between the openings. The distance between the openings from the middle of one to the middle of the other opening. That takes care of another variable in both equations. Next, we have L. L, which I'm going to label as a capital L, as opposed to a lowercase, is a distance from the barrier, or the openings, to the screen. So far, so good, right? The tricky ones are X, theta, and N. X, theta, and N. X is, well, X can be pretty much whatever distance I want, from this maximum to this minimum. Or it can be from this maximum to this maximum. Or it can be from this minimum to this maximum. X can be whatever distance, measured in meters, that you want, as long as N is consistent with it. What would N be in this first case here? Going from here to here. What would N be? 1.5. Right, we're going from 0.5 to 2, N is 1.5. What about, let's go this one here, from 1 to 2 on the other side, N would be 3. From 1 to 2 is 3. And what about N right here, from 2 on one side to 1.5 on the other? N would be 3.5. So you're good there. You're good for any of those values of x as long as your value of n is consistent with your value of x. Theta, that was a poor choice of color. Let's go with orange here. Theta can be this angle measured from the central maximum, central bright spot, central antinode, central constructive interference to the first order, or first order maximum, or it could be to the second order minimum. It doesn't really matter as long as n is consistent. What would n be right here? From 0 to 1, n is 1. From 0 to 1.5, n is 1.5. Okay, make some sense? Okay, let's take a look at these two equations now that we know what each of the variables means, okay? And let me tell you that this equation that we see at the top here, d sine theta, that's the best one. Okay, that's the best one because that is always valid. Always valid, no matter what, no exceptions, as long as you have the angle as measured from the central maximum. The second equation is actually not a real equation. It's an approximation. It's an approximation that works very, very, very well if the angle involved is actually quite small. If theta is less than 10 degrees. If theta is less than 10 degrees, then it's still an approximation, but it's a really good one. If theta is above 10 degrees, then it's not as good of an approximation, so we don't want to use it. It's okay to use this. If you're below 10 degrees, you'll get the right answer. If you're above 10 degrees, the answer starts straying a little bit more from what we should end up getting. Now, I have a little rule of thumb, because to me, like, when they publish our program of studies and they show us, what we got to teach and so on, they say, look, basically, make sure they don't use this if the angle is greater than 10 degrees. Well, to me, when I look at that, it's like, well, okay, so you mean I got to check every time to see what the angle is? If I'm not given the angle, I got to find the angle and make sure it's less than 10 degrees. If I have the angle and it's less than, well, why wouldn't I just use this? And if I got to find the angle to see if it's under 10 degrees, then, well, why wouldn't I just use this? So I have a little rule of thumb that it doesn't always help us to avoid finding the angle, but it does most times. Helps us to avoid finding the angle, okay? So here's what I'm going to say is your rule of thumb. This equation will absolutely work if L is greater than 10 times x. So if you take your value for x and multiply it by 10, and L is bigger than that, you are 100% for sure good to go with that equation. Now, if you find that L is, oh man, it's so close, L is almost greater than 10 times x, well, now you got to find the angle. And you might still find it slightly less than 10 degrees, but you got to find it anyways. Okay, a rule of thumb errs on the side of caution. So our angle may be like 9 degrees, even if our rule of thumb doesn't work, but it's better than having to find the angle every single time, right? Okay, make sense? Always, sometimes. Usually it's okay, but we got to do our little rule of thumb check to make sure. All right, let's take a look at a problem. Example number 1 says monochromatic light. What's mono mean? One color. You're going to see tomorrow what happens if we have more than one color. It's not a big deal at all. In fact, as much as it might bother you when you see it, like all these different colors, you end up treating it exactly the same way. You just got to be careful of something. Monochromatic light shines through 2 slits, producing a third order bright spot 9.5 millimeters from the central bright spot. What is that? That distance from the central bright spot. What is this 9.5 millimeters? That's x, right? Look back here, that's the distance from the third order maximum to the middle bright spot. That's the value of x. Now I'm going to convert that to meters. 0.0095 meters. Oh, listen, as soon as I write down x, or as soon as I write down theta, I want to make sure that I write down the value of n to be consistent with that. What would n be here? From the central maximum to the third order maximum? 3, yeah. Now, sometimes we have a little bit of trouble with that, especially if it's involving a minimum. It's a 0.5. Sometimes there's value in sketching it. Central maximum. First, second, third order maximum. Difference between 3 and 0 is 3, yeah. Now, it becomes especially useful to sketch this out if you're talking about, say, the first order maximum and the third order minimum. Right now you can see the benefit of sketching it, right? First order maximum, third order minimum, that would have been, n would have been 1.5 in that case, right? Easier to see when we sketch this out. We're going from 1 to 2.5, so it would be 3.5. What did I say? Should be 1.5. Is that what I said? Yeah. But here we're 3, because we're going from 0 to the third order maximum. Okay, what is this value? 0.15 millimeters. What is that? It's a little d, yeah? I'm going to convert that to meters right now. 0.15 times 10 to the minus 3. I could move the decimal place, but 10 to the minus 3 is easier, I think. 90 centimeters away. That's 0.90 meters, by the way. What variable is that? That's L. We want to find the wavelength. If you look at your two equations that you have, that I wrote down on the previous page, looks like this is the one that I want to use, right? XD over N times L. That's on your data sheet, by the way. Right? Like, that fits best, right? Okay, but we got to do a little check, because this one's only valid if the angle is greater than 10 degrees. What's our rule of thumb? Is L greater than 10 times X? Is L greater than 10 times X? What's the value of X? 0.0095. Multiply it by 10. 0.095. What's L? 0.9. Is L greater than 10 times X? Yeah, so we're good there. X is 0.0095. Now it's pretty straightforward, right? Times D, N, and L. And it doesn't have to be in meters, but I would recommend meters for these ones. As long as you're consistent, you can get away with anything. But the units for your answer are usually either nanometers or meters, so I just go with meters the whole way. Yeah. We get 5.3 times 10 to the minus 7 meters. That's our answer. Hey, just a quick little aside. What if L wasn't greater than 10 times X? Then you would have had to find theta. Use the other equation. We don't have theta, so we got to find it. If this is X and this is L, then you could find theta there, right? Tan theta is equal to X over L. And you could get theta, and then you could use that other equation. We don't very often have to do that, but be ready for it in case you do, okay? Okay, I got one more example, then we're going to wrap it up here. Monochromatic light, 589 nanometers. That's a wavelength. I'm going to say 589 times 10 to the minus 9 meters. 2 slits. Second dark spot from the central bright fringe. Theta is 15 degrees. Hey, we couldn't use that other equation even if we wanted to, right? But if we have theta, why would we anyways? What's N going to be? Central bright spot. Second dark spot. central bright spot, second dark spot, n would be what? 1.5. Oh, what angle is the third order maximum? Whew. We'll call this the angle of the 1.5. This will be theta 3. Here's what I'm going to do first. This is a tough question. I'm going to say lambda is equal to d sine theta over n. And the only variable I don't have here is d. That gives us a value of d of 3.41358 times 10 to the minus 6 meters. I want to find the third order maximum now. Isn't d going to be the same? Like the distance between the slits isn't changing, is it? So now let's say, what are we looking for here? We're looking for theta this time. So rearrange this to solve for theta. Hold on 2 seconds here, guys. We just solved for d. What would n be here? 3. And what would lambda be? The 589 value, right? You solve for theta. It works out to be 31 degrees there. Does that make sense? Let's do another example. This one's a little bit different. This one says monochromatic light, monochromatic, one color still. We'll deal with polychromatic light in just a few moments here, but for now, still monochromatic, one color. Shines through 1,000 line per centimeter. Diffraction grating produces a first order maximum, 32 degrees from the central max. What's the wavelength of the light used? This sounds like one of those double slit. We call them Young's double slit, named after Thomas Young performed this experiment for the first time. This sounds like a Young's double slit experiment, but yet something's weird here. Usually we have two openings, two slits, two lines, and we measure the distance between those openings to get little d. Here we don't have the centimeters in between lines. Here we have the lines per centimeter. So what do you think this corresponds to? There's not two lines a certain number of centimeters apart. There's a certain distance with a certain number of lines per distance. This isn't d. This is 1 over d. Does that make sense? It's the inverse of d. It's not the centimeters between lines. It's the lines between centimeters. Now, we got 1,000 of these things. 1,000 openings per centimeter versus 2 openings total. We end up getting the same pattern, effectively the same interference pattern. The mathematics is the same. You just have to recognize that the value you're given here is not little d, but rather it's 1 over little d. So from that, you're going to get little d, and then just do your thing, whatever we did for the last couple of questions here. So what do we have given to us here? We're going to say 1 over d is equal to 1.0 times 10 to the 4 lines per centimeter. We're going to say that theta is equal to 32 degrees. We're going to say that n, because we just got theta, n is equal to what? First order maximum, central maximum, n would be 1. What's the wavelength? Okay, let's get d. If 1 over d is 1 times 10 to the 4, then d is going to be 1 over 1 times 10 to the 4. The easiest way to do that is to take a calculator. 1 times 10 to the 4, right? 10,000. Flip it over. 1 over. Gives us 1.0 times 10 to the negative 4. But what units do we get there? centimeters, which is 1.0 times 10 to the minus 6 meters. Does that make sense? Go to meters, but listen, don't convert lines per centimeter to lines per meter. Convert lines per centimeters to centimeters, and then convert it to meters. Why do we not want to find lines per meter right away? How do you convert centimeters to meters? Centimeters to meters is divide by 100, right? But if it's centimeters on the bottom, you're not going to times it by, or divide by 100, you're going to multiply by 100. So it's backwards, right? Let's get it on the top first. Let's get centimeters on the top, and then convert it to meters by doing what we always do, dividing by 100. Okay, what do we got here? Lambda is equal to d sine theta over n. Now it's just like all those other questions we had. D is 1 times 10 to the negative 6 meters times sine of 32 degrees. And we divide that by n, which is just 1. We're going to get a wavelength of 5.3 times 10 to the negative 7 meters. 10 to the minus 7 looks like I'm probably on the right track, right? Not always, as we saw when we went over the examples there, or the homework questions. It's not always 10 to the minus 7, but it usually is. Have a look at worksheet number 19 now. Number 5, 6, and 7, at least for the time being. I promised you a little while ago that we would deal with polychromatic light if we had more than one color. All the questions that we've dealt with so far, including the 3 examples and including the 7 or 8 questions on the worksheet that I've assigned to you, have involved monochromatic light, one color light. What do we do if we have more than one color? Well, the good news is I'm not going to give you any more practice questions just because we're starting to do polychromatic light. The good news is we end up solving it the same way. You just have to understand something as we go through it so that you end up solving it the right way. Okay? If we have, let's say, red laser light, monochromatic red laser light going through this 2 slits or this diffraction grating of 1,000 slits per centimeter or whatever the case may be, we will get a series of bright spots, dark spots, bright spots, dark spots like this. Okay, this is exactly what I've shown you for the last number of days. This is what we will get. If we have monochromatic light that is a different color, different frequency, let's say orange, then we will get a similar pattern. But there will be one difference, and that is the position of each of those maxima. If we look at the equation, lambda is equal to xd over n times L, then we see that lambda and x are directly proportional to one another. Lambda and x are directly proportional to one another. So in other words, as lambda is bigger, x is bigger. As lambda is smaller, x is smaller. All right. If we go from red to orange, I know that's not a very good orange, but it's supposed to be orange. If we go from red to orange, then that means the frequency is increasing. Red, orange, yellow, green, blue, indigo, and violet. The frequency is increasing, therefore the wavelength has decreased, right? If the wavelength has decreased, what would you expect to happen to the value of x, the distance between maxima? It would decrease. Well, take a look at this. It's not much different, but you do see a little bit of a difference here, right? These maxima for the orange are closer together than the maxima for the red. Now, we're still dealing with monochromatic. The first experiment, monochromatic red. The second experiment, monochromatic orange. But I just want to illustrate what happens if you have 2 different colors at different times before we look at what happens if you have 2 different colors at the same time. Okay, does that make sense? If we switch to yellow, we get a similar phenomenon taking place, right? Higher frequency, smaller wavelength still, and that means smaller x. So they're going to be closer together, and so on and so on and so on. Until you get down to blue and indigo and violet light, we're decreasing our wavelength even more. That means, Aiden, the value of x is going to be even smaller. Okay, so 5 different experiments here with 5 different monochromatic colors. 5 different monochromatic frequencies here. Make sense? What happens if I send all 5 of these through this 2-slit or this diffraction grating with 1,000 slits per centimeter or whatever? What happens if I send them all through at the same time? In other words, what happens if I have white light, which is all the colors going through at the same time? Like I did over here in my poster, right? My Pink Floyd poster. White light goes through a prism. Well, now we're sending white light through this diffraction grating. What happens? Well, it will split it up. It will split it up as similar to what the prism did, but for a different reason. Instead of refracting at different angles, it will diffract at different angles. And it will split up white light, which consists of all of these colors, into individual colors: red, orange, yellow, green, blue, indigo, and violet, because each different color refracts differently, but it also diffracts differently. Now, take note of this, though. With refraction, red light refracted the least. Okay? If this is our central right here, our central maximum right here, we would say red light refracts the least, but red light diffracts the most. So it's opposite, right? Instead of getting Roy G. Biv, we get Viv G. Yor. Or the opposite of Roy G. Biv. Red light refracts the least. Blue or indigo or violet diffracts the least. Okay, so what is it actually going to look like if I end up putting white light through these two openings or through this diffraction grating? It splits it up, but it doesn't split it up to look like this. Right? You're not going to get one line of red, one line of orange, one line of yellow. Rather, these will be superimposed over top of one another. So what you end up getting is, here's a little bit of a simplified version of it, the handout that I just gave you here. You will get a central maximum that is white. It is all the colors together because it hasn't diffracted there. Now, your first order maximum, let's just look at the one side here. Okay, this is my central maximum, or as a number of 0 assigned to it, right? My first order maximum is this. It's not this one. It's not this one. It's both. My first order maximum consists of both of the colors. Notice that blue light diffracted the least, red light diffracted the most. Opposite to what we had with refraction. This is the first order maximum. Okay, then we have the second order maximum over here. Again, blue light diffracted the least, red light diffracts the most. Okay, realistically, what we often end up seeing is this white light with a rainbow here corresponding to the first order maximum, and then a rainbow here corresponding to the second order maximum. Why is it fainter? You guys remember that intensity graph, right? The further away you get, the lower the intensity. Okay, but it's still a rainbow, right? But it's a rainbow not Roy G. Biv, it's a rainbow Viv G. Yor, or backwards to Roy G. Biv. Okay, does that make some sense? Now, how do you deal with it mathematically? This is the important part here. Or, it's all important, but this is the part that ends up making this easier. If you get a problem where you've got multiple colors on your interference pattern, here's what I want you to do. Okay, look at the top diagram here. Multiple colors in this interference pattern. If you're given data for blue, then what I want you to do is pretend red doesn't exist. Like literally wipe it off the face of the map. If you're given data for blue, pretend red doesn't exist. If, on the other hand, you're given data for red, then wipe blue off the face of the earth. It doesn't exist. As far as you're concerned, it's dead to you. If you're given data for both red and blue, pick one. Pick one. Doesn't matter. If you're given data for both red and blue, pick one. I don't care whether you go with red or you go with blue, but don't ever try to do one of these diffraction interference problems with more than one color. Pick a color. And the obvious one to pick, hold on for 1 second, the obvious one to pick is the one for which you have data. If you have both, doesn't matter which one you use, but just use one of them. Now, just be careful here, quickly before you pack it up. Look at this side again. Be careful. This is our central maximum. First order maximum. This is not the second order maximum. Okay, third order maximum, fourth order maximum. That's not what it is. This is the first order maximum. This is the second, because we're picking one color, blue. Or, right, because remember, red is dead. Or you could have said blue is dead. This is the first order maximum, and that's the second order maximum. But don't ever start counting all the lines and make them each a maximum. It's one color or another, and then go with it the same way as you dealt with all the other 7 questions on that worksheet.